Now let's take a look at this example of a limit of a radical function. Here our function is x plus the square root of x squared plus 2x. And we're taking the limit of that as x approaches negative infinity. So it's useful to, again, it's useful to kind of think about, it's not exactly direct substitution because x is not going to a number, but something like that. If we think of, okay, just what happens with this if we try to let x tend toward negative infinity? Well, a very large negative number squared is a very large positive number, but this will be a very large negative number. So there's the question of what happens when we combine those two, adding a large positive number and a large negative number. Do they balance out somewhere in between, or does one of them overpower the other? You might expect that the x squared overpowers the 2x, and in this case it does turn out that this expression x squared plus 2x does approach positive infinity. You can work through that using the methods shown for dealing with polynomials and some of the other examples in the textbook. So then the square root of that will turn out to approach positive infinity. But here we have x approaching negative infinity, and it's not clear what's going to happen between those two. We have a negative infinity plus a positive infinity. And because it's a square root of an x squared, these are approximately the same kind of magnitude, and it's a little bit, it's uncertain what'll happen with those. So we're going to have to, be a little bit more precise with this and figure out what's going on. Let me recopy this. That we're going to modify it a bit. We saw in my previous video or in the other examples from the textbook that when you have a rational function, you can pull a little trick with the, with division, basically, and kind of shuffle powers of x around to get it into something that's better behaved, right? So let's do that here. We don't have a fraction as written, but let's go ahead and write this as a fraction. And just trying things out here, let's multiply by the conjugate and see what that does for us. So we'll multiply numerator and denominator by the conjugate of that expression. So that is x minus the square root of x squared. Oops, sorry, that's a plus 2x. We don't switch the sign of what's inside. That should be copied exactly. We have, since we have x plus the square root of this stuff, we have x minus the square root of that same stuff. Okay. And let's do a little bit of algebra here, just multiplying and simplifying. So we have x plus the radical times x minus the radical. It's a product of a sum and a difference is a difference of squares. So that is x squared minus that radical squared. So that will give us just x squared plus 2x. That is divided by x minus the square root of x squared plus 2x. Okay. And that is the limit as x approaches negative infinity of the denominator is longer. I'll write that first. X minus the square root of x squared plus 2x. And that is underneath. So we have x squared minus x squared is 0. Minus 2x, we have a negative 2x up here. Okay. So we've simplified that as far as we can. Now let's try that trick like we used with rational functions, ratios of polynomials. This isn't a polynomial down here, but we can still do some of the things we would with it. We again want to find the largest power of x in the denominator and take that out of the numerator and denominator. So, in this case, if we have x to the first, here we have an x squared, but the x squared is inside of a square root. So that actually counts like x to the first in terms of what we're doing here. If you'd had a square root of x cubed plus something, whatever, then that would be like x to the 3/2 power, right? Because you're taking the square root of the cube, right? Now, we cannot take the square roots of these terms individually. We're talking about asymptotic behavior as x approaches positive or negative infinity kinds of things, right? Do not, the radical does not break apart across addition. That doesn't give you the right results there. I'm just talking about how we kind of loosely figure out what kind of powers we're dealing with, right? Actually, I suppose one thing that you could do if you weren't sure is you could start with just whatever's in the radical and find the highest power in the radical and factor it out and simplify, and then look at what's left outside the radical and take the highest power of that. That'll work out just fine. So let's look at this. Actually, you know what? We're going to have to do that anyway, so let's go ahead and do that here. Knowing that we want to take out that x to the first, now we have to do one of those things like we talked about in the previous video, where we need to divide that out of the numerator and denominator. And there are 3 ways to do that. Of the 2 approaches that I showed last time, I think by the second approach, the one that I don't usually use, is the easier one here. It's the easiest one to think of. So here's a case where that is particularly handy. So let's start by factoring out that x squared from inside of here like I was talking about, and we'll see what happens. So we have the limit as x approaches negative infinity. We'll copy this here. So this is x minus... Actually, let's just make this an aside. Let's break up the equality here. I like to keep the equality, but I'll have several steps without other things. So let's just make this an aside. Let's just look at the square root of x squared plus 2x and do some manipulations there. Okay. So you'll note that since I don't have an equal sign, this is starting a new sentence, basically. Let's factor out the x squared inside the radical. So that leaves us 1 plus 2 over x, right? Now we have a square root of a product, so we can write that as the square root of x squared times the square root of 1 plus 2 over x. Now we need to simplify the square root of x squared. And I'm sure many of you have an immediate impulse at this point that, oh, well, a square and a square root are inverses, so that just cancels out and we get down to x. But that's not necessarily true. And let's examine why. Let me start with just a numerical example. Suppose we have the square root of 3 squared. If we evaluate this, we start on the inside. 3 squared is equal to 9. This square root symbol means we take the principal square root. The principal square root of 9 is 3. So the square root of 3 squared is 3. No problem. But suppose instead of 3, we had negative 3 that we were squaring. Square negative 3, and you get 9. Take the square root of that, and you have 3. That is not the same thing we started with, right? If you take 3, square it, take the square root, you get 3. If you take negative 3, square it, take the square root, you get positive 3. So what happens here, the problem is that squaring is not a one-to-one function. Once we square a number, the result tells us the magnitude of the original number. It's the squared magnitude, but we lose the original sign information. We know how big the number was, we just don't know if it was positive or negative starting out. So if you square a positive number and take its square root, you get back to that positive number. If you square a negative number and take its square root, you get back to a number that has the same size but opposite sign, right? So in other words, we have a function here. Let's put it this way. The square root of x squared can be defined by a piecewise function. It is either x or it's the opposite of x, right? It gets back to x itself if x is non-negative, and it becomes the opposite of x if x is negative, right? Keep in mind that this does not mean a negative number, it means the opposite of what follows. So if x is a negative number, then negative x is positive. So this is a relatively simple little piecewise function. It's also one that should be familiar to you. If you don't immediately recognize it, maybe pause the video for a second before I go on. See if you can figure it out for yourself, if it looks familiar. And hopefully if you think about that for a little bit, you'll recognize that this piecewise function is the definition that we usually give for the absolute value of x. Right? If x is non-negative, it's its own absolute value. If it's a negative number, you switch the sign that makes it positive, and that's the absolute value. And we see that's what's happening here, right? Whether you start with 3 or negative 3, when you square and then take the square root, what you get back to is the magnitude, the absolute value of the original number, but without the sign information. We don't know whether the original was positive or negative at that point. So coming back to this, we have the square root of x squared is the absolute value of x. Now, this absolute value is a little bit difficult to deal with, especially since we're trying to cancel some stuff out. We can't bring the x out of the absolute value just algebraically. We need to try to resolve this. This sort of pattern shows up a lot whenever we're taking a limit to positive or negative infinity of an expression with a square root or a fourth root, any of these even powers, we'll end up with this kind of absolute value stuff very frequently. And fortunately, when we're taking that limit, we know what we can reasonably assume about x. We only care about this expression in the context of this limit, which is as x approaches negative infinity. That means x is a very large negative number. What this function does when x is positive is completely irrelevant to our concerns here. We want to know what is happening when x is negative. So we look at this and we can say, okay, well, we can just assume that x is negative. And if x is negative, then its absolute value is its opposite. So that is negative x times the square root of 1 plus 2 over x when x is negative. Right? So that means that the limit that we had above, not positive, negative infinity, the limit as x approaches negative infinity of negative 2x divided by x minus the square root of x squared plus 2x. That is the limit as x approaches negative infinity of the denominator. Now we had minus this square root, but now we know that what we're subtracting, well, I'll go ahead and write that. We're subtracting this expression, negative x times the square root of 1 plus 2 over x. So of course that'll cancel out to be a positive minus the negative, right? So now let's again factor out the x. So if we pull an x out of the denominator, which I can't do yet because we still have the limit. If we pull the x out of the denominator, our first term is 1. Again, we're subtracting a negative, so that becomes a positive. We're pulling the x out of that, so that is just a square root of 1 plus 2 over x. And this is under x times negative 2. X over x is 1. So the denominator is just 1 plus the square root of 1 plus 2 over x. The numerator is negative 2. And at this point, we can pass the limit into the individual pieces here, the individual terms, using the limit laws. Right? This is a limit of a quotient, so we can take the limit of the numerator as negative 2. In the limit of the denominator, well, we have a sum there. The limit of 1 is 1. The limit of a square root will be the square root of the limit of what's inside. And so we have 1 plus, and as x approaches negative infinity, that's a very large number. 2 divided by a very large number is a very small number approaching 0. So we have that. 1 plus 0 is 1, square root of 1 is 1, 1 plus 1 is 2, negative 2 divided by 2 is negative 1. So that is the value of the original limit. Okay. So that tells us that we have a horizontal asymptote to the left of y equals negative 1. Doesn't say anything about whether there is an asymptote to the right, or if so, what it is. So you might, if you wish, you might want to consider, take a look at what happens to this if you take the limit of that original function as x approaches positive infinity. But there you go, basically. Now, it is possible to handle this using the sort of division kind of issue where we can kind of undo this stuff that we have here. Where, let's see here, we have the expression that was a negative 2x over, what do we have? X minus square root of x squared plus 2x. Negative 2x over x minus square root of x squared plus 2x, yes. Okay. So we can, like I mentioned, we can use the idea of saying, okay, what's the highest power in the denominator? It's basically x to the first because the x squared is inside of a radical. So we can multiply by a fancy one that looks like 1 over x divided by 1 over x, or alternatively, multiply by x to the negative first over x to the negative first. And then when we start to simplify that and distribute it and cancel and things, we have to figure out how the 1 over x is going to interact with the radical. And to do that, we need to write it as a square root of 1 over x squared, but we have to also take into account the how that interacts with the signs, because again, we need to think about whether x is positive or negative. Since x is approaching negative infinity, this 1 over x needs to be negative. But if we write a principal square root, that's a positive number. So we actually want the negative of that, right? And it's that reasoning right there that makes me generally feel that this bookkeeping technique is a little bit less useful when we have radicals. I think with radicals, it is easier to think about pulling things out and simplifying. If we continue this, by the way, one more step, simplifying this a little bit, that is 1 minus a negative becomes a positive. And now you have this square root of 1 over x squared you can push through, and you see that that gives us the same expression that we had from before. That was a little bit over ambitious there. Let's clean that up a little. So that gives us the same result there. But trying to remember, first off, remembering that there is an issue here when you try to turn that into a radical, and secondly, thinking through carefully how we need to replace this in order to make it. This is a little bit counterintuitive to most people. And I personally do feel, and I expect most students do as well, that it is probably easier to think about factoring out that power from the radical, and then just remembering that the square root of x squared is an absolute value of x, which is something that you should know in general. If you're less familiar with that, pay attention to it, and be careful. That will show up throughout the calculus series in random little places as we're simplifying expressions. But that's the general idea there. Yeah. So as a summary, when we have a limit at infinity of a radical expression, if it's already something that looks like a rational function, you could try diving into taking out the largest power of the denominator kind of a thing. If that doesn't work, maybe try multiplying by a conjugate first and then see what happens. If it's not even a fraction to begin with, put it over 1 and multiply by the conjugate so that you get some powers of x in the denominator and then can start shuffling things around. That's kind of the general sort of technique that we use on problems like this.